time. We're going to talk, comrades. We today, comrades, are going to talk about the atom. At the atom. The atom bomb. The atom bomb. You know what I mean, Camden, right? You played that video game. It's a song from the 40s. For the demographics of this channel, many 8th graders, and then everyone else is geriatrics. So these people know about the atom bomb as a song, not from the video game Fallout. They remember dancing to it in the line dance in 1956. So that's also a song, the atom bomb. You remember it from Fallout?
Fallout?
Yeah. Do you?
I'm familiar with the Fallout series.
Yeah, but do you remember the song that says, the atom bomb, the atom bomb? Anyway, that's not what this is about. The atom. The atom. Let's compile our bellwork atoms and think of what we should include in our professional model of the atom that will be demonstrated to Peyton, who has high standards. What should we include in it? Let's make a list first.
It should have protons, neutrons, and electrons.
Okay, and in the nucleus we should include which of those two things?
Protons and neutrons.
Protons, I should say which two of those things? Protons and neutrons. What, Kyla, should be included in both of these?
Quarks.
Quarks. These are made of quarks. These aren't quarks. I did this in a way that makes it seem like, so I'm just going to write made of quarks.
Protons and neutrons are hadrons.
Protons and neutrons themselves are hadrons or hadrons, depending on how you want to pronounce it. What's special about protons and neutrons? Well, lots of stuff is special.
They have a charge.
Protons have a charge, but they both have mass. They both have mass, as all hadrons do. Probably because of a particle called, or more of a interaction particle called the Higgs boson, which lends particles mass. But we're kind of meshing the atom, with quantum mechanics, which is something important for you to know about. It's the way the world's out. I asked a question the other day. I think there's video evidence of this, but one of the 8th graders asked me a question. Why do I need to know this? And the answer is, for one thing, for me, the answer is, why do I, Comrade David Kine, why do I need to know this? I think it's fascinating. This is the way the world actually be. Your whole first section is about the way people used to think it is. You could have a section of your own book called The Way I Used to Think Matter Was. I used to think when I was, let's say kindergarten, so I don't seem like an idiot. When I was in kindergarten, I used to think that I could see the atoms because they would, like when you look in the sunbeam and you can see the dust particles, I was like, those are atoms. I know they are. I've seen Magic School Bus. I know those are atoms. But I was wrong. That was a wrong idea I had about matter. Did it change my life in a way like getting my legs chopped off wood to find out how the atom actually is? No.
Just like there was a whole
But it's still, to me, it's valuable for me as a human being to know the truth about the way things actually are. And this is part of it. This is not the whole truth, but this is part of the truth, and being closer to the truth today than I was yesterday is important to me. So that's my answer for that. But the answer I could and did give that student, that 8th grader, is in this school, it's not about this. It really isn't. It's about you being able to learn something you didn't know and to follow these processes in order to get this result, which in your case is a grade or on a test or something. But ideally, the intrinsic motivation, like what I have, would be there for you too, where you're interested in learning about this because this is the truth, the capital T truth. This is the way the universe is. But if you're extrinsically motivated, then it might be good enough for you just to do this so you get a grade, and that's fine too. And there's something to be said for that, right? If you work at the Arby's and your boss is always slapping you on the face because you put the sandwiches together the wrong way, and you say, well, why do I have to put a sandwich? There's no overarching. The Lord did not come down to Moses on Mount Sinai and say, this is how the Arby's sandwich is. Bottom bun, roast beef, top bun. But that's the way it is. That's the way it is the best, even if that's only subjective. That's the way most people want it, and so that's the way your boss is going to tell you to do it. And it's about following the process. And you could definitely make a case for just like not having to know what the atom's about, not having to have your Arby's sandwich be bottom bun, roast beef, top bun. But it's about the process. Trust, this is the unofficial motto of the School of Mines in South Dakota, is trust the process. You have to show the process to trust the process. That's why I would have you show your work. And you have to know about these guts of science in order to be able to understand the universe. Maybe not fully. You may never, at least on this earth, you will not understand the universe fully. But you can understand it as fully as you can. You know what I mean? Like, you're never going to be able to understand it as fully as it's humanly possible if you don't know this part. And for me, that's valuable. But even if it isn't to you, you still have to do it because I said so. That's what I was trying to tell this boy or girl. Anyway, what else is I got a little sidetracked. I got a little fired up. I'll break this up into chapters, then I'll put what's a good noun to describe what is rant about the importance of education. We'll put that as chapter 2. Chapter 1 was we barely talk about anything. Chapter 2 was rant about education. Chapter 3 is more about the atom. What else has the atom got in it? What should we include in our model of the atom?
Electrons.
Yep. Electrons, which are leptons. These are a kind of matter called leptons. There are other kinds of matter. Leptons, hadrons, those are the ones that most normal matter is made out of. There are neutrinos, there are muons, there are gluons, there are others that I can't remember the name of. But these are the things that normal matter is made out of. What's true of electrons?
They have a negative charge.
They have a negative charge.
No mass.
Not quite. They technically have mass, but it's exceedingly tiny. It's exceedingly tiny. They have a tiny, tiny mass. In fact, at this scale, we talk about their mass usually in terms of something called electron volts, which you'll recognize as a unit of electrical current. No, electrical potential. And the reason that works is because on this level, forces, or energy, and matter are kind of interchangeable. The quarks that make up these hadrons only account for something like between half and 2/3 of the mass of the hadrons themselves. The quarks, which make them up, only account for between half and 2/3 the mass of the hadrons. The rest of it is the energy that holds them together, gluons. At that scale, the tiniest scale in the universe, at that scale, energy is maybe not equivalent, but interchangeable with mass. And so having energy in there makes the mass greater as well. Same thing for electrons. We measure their mass in electron volts, or milli-electron volts, or mega-electron volts, or anything like that. Now we have what we're going to put in there. How should we do it, and what should we label this? Let's start with a label, which is not usual, but in this case we're going to. What should we label our atom model? Pick an easy one, please. You're looking in the right spot, though. Let's do
Ugliness.
No, let's not do ugliness. Lithium, but we're not being specific enough. We have to say lithium.
Whatever the mass is.
Let's do 6 because it'll be easier. What does the 6 mean, and why will that make it easier?
It has
That's
6
the mass, so it has 6 neutrons.
Yes, so let's label this. Let's label our title first. What is this?
element.
Yes, this is the element's name. And what is this?
It's
Mass.
atomic mass number.
Yeah, we're just going to call it mass number. So this is how many protons are in there, right?
Nope.
Nope. Good, thank you. I love it when I ask a question but the answer is no and someone says no. Freshmen are real bad about it. Freshmen are really bad about this. I will say a question like, this is the number of protons, right? And they're all just like taking those, like, yep! And it isn't. This is not the number of protons. This is the number of all the massive particles, what I'm indicating broadly over here. Which ones have mass?
Protons and neutrons.
Yeah, we have a term for those now that we're adults.
Hadron.
Hadrons have mass. This is the mass of the hadrons together. So I just divide it by 2 to find how many protons there are, right?
Wrong.
Wrong. That's not how I do it. In this case, that would give me the right answer, but that's not how I do it. That's not the process. How do I do it?
You look at the periodic table.
I look at the periodic table of the elements, and I find that there are, in lithium, how many protons? 3. 3 protons. And therefore, if its mass number is 6, which means there must be 6 hadrons, there are 3 protons. What's the only other kind of hadron there is that makes up normal matter? Neutrons. So how many neutrons must there be?
3.
Neutrons. 3. I like the reason that the reason I like what you chose, Mitch, is because it illustrates that we can't, a shortcut would seem like we could just half this, but that's not always the case. And you illustrated to us that that is not the case by making me say this, and then the answer was no. Anyhow, what else should we say about this? Rewind. An atom must be what? And we sometimes specify, we don't have to because of the definition, but we sometimes say a neutral atom What's true of this? Must be neutral. Yeah, what's that mean though?
You can't have a positive or negative charge.
Yeah, no charge. What do we call it if it does have a positive or negative charge?
Isotope.
It's no
Or
ion. It's called an ion. This is an isotope. An isotope
I guess.
has a specific number of neutrons. What would be another example of an isotope of lithium? Another isotope of lithium. Just make one up. It may not even. Lithium-7 may exist, it may not. I don't know. I don't know all the isotopes. But an isotope is a specific arrangement of protons and neutrons. An atom must have no charge. So that tells us what? If it has 3 protons, what's its positive charge?
+3.
Plus 3. What must its negative charge be to match?
-3.
Minus 3. So how many electrons must it have?
3.
3. So this is always the same as neutrons, right?
Wrong.
No.
Wrong. Electrons is not always, it's always the same as protons, right? Only
Only
if,
in atoms.
only in atoms. If there's a charge, what do we call it?
An ion.
Ion. Ions have charge. Ions have charge. You'll sometimes, I will make this mistake, you will make this mistake, many people make the mistake and just glaze over it. We will say an atom of lithium-6 plus 1. We're technically wrong. We should say a lithium-6 plus 1 ion, or an ion of lithium-6 plus 1. But even throughout this year, and if you look back at the videos from last year, I will continually talk about the atom even if it has a charge, when we should be using this word ion. Ions have charge. So it's kind of on the border of, your book will say it. Your book will say charged atoms are called ions, even though that's technically not true. Atoms must have a neutral charge. It's kind of on the edge of right and wrong. It's kind of like ain't is technically incorrect to say, but people say it all the time and everyone understands what it means, and so it's kind of on the edge of right and wrong. Where if you make up a new word, blah, 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 and that's what you're going to use to say no from now on, then no one's going to know what you mean, and you're just flatly wrong. Same as using isotope when you mean ion or atom. Anyway, now that we have what we need to put in here, almost, really this is going to be the whole lesson in one diagram, and I like that.
This is good.
This is good. This is elegant. Maybe it's not the best, but it is elegant. Let's. I'm going to use 2 different colors here. What's a good up color? Blue. What's a good down color?
Brown. No. Brown. Red. Red.
Bye bye.
Oh.
Ooh, let's use purple and cat throw up. So we'll have quarks real quick. Let's make a little side note. We love side notes. I love side notes. You don't have a choice. Quarks. There are 6 quarks in the universe that have been discovered. As of the publishment of this video, what are they?
Up one.
Up, down, and it's like a strange or something like that.
I'm thinking in a specific order. So, comrades, what are the other quarks? Kyla's got it.
Top, bottom.
There you go.
And charm.
Charm. I put them in this order specifically because this is, if I remember right, look this up later. Like, comment, subscribe. Put a comment about whether this is, you can't actually, the comments are turned off because I don't want people coming in here with their, check out this link for my sexy vids or whatever, which is something that did happen on some of the other videos. It's like some spam bot from Turkey putting in that kind of crap. But anyway, if I remember correctly, I think these are in order from least massive to most massive, and they kind of alternate. Up has a positive charge, down has a negative charge. Top is significantly more massive than up, but it has a positive charge. Bottom is the same way, but has a negative charge like down. Strange has a positive charge, and charm has a negative charge. Is that right, Kyla?
It says up, charm, and top quarks have a charge of plus
Oh.
23e.
Okay, so the charm and strange I have switched around. Thank you. I always listen in that order, but I'm going to switch them now. Charm and strange. So charm is positive, you say.
Yes.
And then down, bottom, and strange have a negative charge.
Yeah, negative 13.
Okay, and then up, it goes in this order. Up is least massive, top is middle, and then charm is most massive. Is that right? Is that what your little data shows there?
I I would assume so. Let me click on it.
Wikipedia.
Yep.
Yeah, which is
Fantastic site.
fantastic site. Like, comment,
You
subscribe.
thought I was gonna.
Yeah,
bash
You want me to look at their
I had my
maps,
eyebrows
right?
up already to tell you about it.
Already
Yes, I
going
want to
right
hear
on
it. Yeah.
chapter 4.
Okay. What? This is what it's saying. That's their little table they got.
So actually, top is the most massive, and bottom is the second most, and then charm and strange. Very interesting. So it should be, if we were having them in order, leave that up because I want to be able to look at it. We should have, did I just say top is the most massive?
Yeah.
Yes.
And bottom is next most? So what I had said earlier was complete bottom, I'm going to spell with a U. Here I am talking about quantum physics, like, bottom! Anyway, and then, charm was more massive or strange is more massive? Charm is more massive.
Do you have whiteout I can use?
This is in order of increasing mass. Increasing mass. Please don't write a pin in my class, Camden.
I thought we were supposed to.
I'm just kidding. Increasing mass. Up, down. Which one was positive of our colors that we picked? Purple, like grape, which I hate, is positive. So I think up was positive.
Some people call it Nintendo.
Some people
No, here, I'll go back here. It's up, down, up. Here, if we go back like this. One more.
I'm 7'4".
It says up, charm, and top.
Okay, so up, charm, and top are positive. So up,
I'm 7'4".
charm, and top are positive. And then down, strange, and bottom are negative. And we're not going to get too deep into how much positive or negative, but what I want you to know, because they're the ones that make up hadrons, that up have a charge of positive 2/3, and down have a charge of negative 1/3. These ones also have charges, but don't worry too much about those. These are crazy things. There's an idea, and you can watch YouTube videos about this. Other video streaming platforms are available, but you can watch videos about this. It's hypothesized that if there was any strange matter, macro scale strange matter in the universe, that it would somehow be more stable than baryonic or hadronic matter, and that if even just touching strange matter would cause normal matter to change into strange matter. So possibly the universe could end with everything being strange matter, which is kind of like the King Midas effect. Like the strange matter would turn this into strange matter, and that would touch that, would turn that into strange matter, and eventually the whole universe would just be strange, which is kind of interesting. I don't know what the evidence actually suggests, but it is interesting to think about. But anyway, these ones make up normal matter. All normal matter, what we call normal matter. Who am I to say? There might be somewhere in the universe or some of the universe where this isn't the case, but we consider this, what's sometimes called baryonic matter. Let's not use that word because I might be wrong. Let's just put normal. Normal matter. Normal matter. I was trying to sound smarter than I actually am. Let's just put normal matter. So then these charges work out neatly. There must be 3 quarks making up a hadron. So, using these neat little charges, what would make up a proton, and how can we tell? I'm going over here to our master drawing, which is the first time I actually added something to it. 2 ups and 1 down, held together by what?
Held together by, wait, I have this written down.
Yeah, we all should know though. The strong nuclear force. Held together by the strong nuclear force. Make up 1 proton, because if you see, plus 2/3 is 4/3, minus 1/3 is
3/3, which is 1.
Which is 1. So it has a charge of plus 1. So this little boy is a. There's not actually probably a circle around them, but that just didn't help us keep them together. That's a proton. What is the only other way? Okay, for some reason, something about color charge. We can't have a particle made of 3 up quarks. So eliminate that. Same thing with down quarks. So what's the only other configuration we can possibly have?
2 downs, one up.
2 downs, 1 up. 2 cat throw-ups,
One
1 beautiful purple.
magenta.
Some people call it magenta.
I call it.
I call it purple. So what's that guy? Well, minus 1/3, minus 1/3, what's that up to? Negative 2/3 plus 2/3, 0. So he has a charge of 0. What might be true of their masses, as far as we could tell?
Or this.
Probably should be the same. They're very, very, very close to the same. On the order of 1/10,000,000th, I think, of the same. They're very close to the same. They're more the same than human being twins are the same. We usually just say they have the same mass. So now I have, in my diagram of lithium-6, which will be on the quantum level, I have a proton and a neutron. And what are those held together by? The strong nuclear force, yes. The strong nuclear force acts between hadrons, just like it acts within hadrons. Okay, what do I need to add now? Well, I'm trying to make lithium-6, so I have 1 proton and 1 neutron. What do I need to add?
2 more protons.
2 more protons. Let's put them like that. I could draw them the same way, but it's going to take forever, so I'm not going to. And 2 more neutrons. Pretend these all look the same. Pretend they all look the same. Whoever's watching this, creepy Turkish person. Pretend they all look the same. They are all made of quarks. I just did this for quickness. And this whole blob here is called the nucleus. And it all together has a what kind of charge?
Nothing. 0. Or no, +3.
Yeah, this all together has a nucleus, or has a positive 3 charge. So how come, since you know this, if you have a negative end of a magnet, it repels another negative end. If we have 2 electrons, they repel each other. How come this doesn't fly apart? They're only positive or neutral. How come they don't fall apart?
Because the force is strong.
The strong nuclear force is stronger. What is also true of the strong nuclear force? It's a shorter range. So if we get this is all extremely, extremely small. This is the smallest things can possibly be in the universe. If we get on even slightly larger scales than that, like instead of having 3 protons and 3 neutrons, if we get up to 80 protons and 80 neutrons, so not even that much bigger,
That's why they're unstable.
the strong force runs out, and that's why it becomes unstable. And so the electromagnetic force takes over, and they fly apart, and that's called radiation. Unstable nuclei, that's the plural of nucleus. Unstable nuclei come apart through nuclear radiation. And there are 2 ways an atom can be unstable. All atoms with an atomic mass greater than that of bismuth, so greater than 208 it looks like, are radioactive because they're just too big. They're just too big to stay all together permanently, and so they fly apart. But also, almost every atom, I think except for iron, has unstable isotopes. So there's some arrangement of this that is unstable too, and that has to do with the ratio of neutrons or protons. So the neutrons are here to kind of act as a buffer between the protons. You can think of it that way. Whether it's a design purpose or whether that's just the way it be, doesn't really matter at this point, but that is how it is. The neutrons help keep the nucleus together because they operate with the strong force, but not with the electromagnetic force. So they're acting to glue. In fact, that's why we use the word gluons. They act to force the other nuclear particles together, but they don't have the repulsion that protons have because they have no electrical charge. They have no negative or positive electrical charge. What else should we draw on our little diagram here?
We better draw some electrons.
We better draw some electrons. And how should we orient these electrons? In reality, what would we draw?
They're going to be outside the nucleus.
Away from the nucleus, at least partially. They're not
Around
touching
like
the
a
nucleus.
little...
But what holds them towards the nucleus?
The force.
This force that held these together is the what?
Strong force.
Strong nuclear. Well, that really shows up good. Strong nuclear force. One of the 4 fundamental forces of the universe. And then the rest of these little guys are held on by what? These are electrons. They're supposed to be electrons, which are leptons. They're the symbol E minus. They have a -1 charge.
Weak nuclear?
No. The electromagnetic force. which acts over much longer ranges. I'm going to actually spell that out on the other one. Acts over much longer ranges. It acts on macroscopic ranges. You can see the electromagnetic force operates even on macroscopic. Like if you have a magnet, you can see it attract another magnet. That's macroscopic. It'll attract it from 20 centimeters away. And so it operates over much larger distances, but it's not as strong. Electromagnetic force. And so if we were being we could imagine this as a snapshot of the atom frozen in time. We have a nucleus in the middle, which is significantly larger than the electrons, which are on the outside. And then if we resumed playing it, what would happen to these in the very next instant? In the next Planck time, the very shortest amount of time that could possibly occur, what would happen to these electrons?
They disappear in those.
Yeah, they teleport. They stop existing here, and they start existing somewhere else within their probability field. They're more likely to exist here in this, what we call an orbital. This is the area in which they're the most likely to exist. This orbital happens to be 1s1. Oh, sorry, just 1s. The 1s orbital. It has 2 electrons, so we'd actually call it 1s2. Is it possible for them to exist elsewhere? Yeah, sure. We resume playing, and maybe one accidentally exhibits itself outside of here. Fine. Maybe one gets very close to the nucleus. But the forces still act on it. And so it's repelled out. Well, actually, it's attracted to this, which is what holds it in. But it can't come inside of here because of laws against touching. No touching. You see my sign I put up today? No touching. But that's also true in the universe, too. These can't occupy the same physical space. They're most likely to exist around here, but they can't be inside the nucleus because there's already stuff there. Same reason I can't have my hand inside of the book, because there's already stuff there, for crying out loud. They're most likely to exist in this area, but they can exist elsewhere. That's why we call it a probability cloud. Probability cloud. How many electrons should I have, though?
3.
3. And that third one is most likely to exist here in this 2s orbital. So altogether there are 3 electrons. We usually draw this, and you'll see this drawn, I will draw it this way several times. We'll usually just draw it like this. There's the nucleus, and here is 1s1, here is 1s2. We just draw them as circles. In fact, we usually just draw the orbitals all together as circles. We'll talk about what these 1s and 2s's mean. In this case, it's 2s1, because there's only 1 electron in it. We'll talk more about what those mean when we get to chapter 5. But for now, realize that in reality, this is how they work, a probability cloud. But we often express them with this, what's called the Bohr model. Bohr model. And these are all vocab words. The models are vocab words, weren't they? Well, maybe not. No, they were not. Most of what the book is actually about is what these models are and how they were determined, which is interesting, but this is what's more important. I do think it's interesting how Dalton and Bohr and Rutherford discovered this was true, and we might talk about that if there's time. But it's most important to me that you know this is how it would be, at least as far as we know. This is what's called the electron cloud model, and it's also called the quantum mechanical. It has to do with the quantum mechanical model. And the main difference between those two things is that we can think of the electron cloud model as a physical model, how they're existing in space, and the quantum mechanical model tells us their nature. These actually are, even the hadrons, are really waveforms. They're excitations in a field. The whole universe is a three-dimensional field of electromagnetic force, gravitational force, strong nuclear force, and these things are just manifestations, waves in that field. That's the quantum mechanical model. But we also think of it physically as the probability model, or the electron cloud model, which it has this probability cloud. The previous model that we most often used was the Bohr model. The main feature of this is that they have energy levels. You see them? Energy levels. We're going to go back in time. I usually present this lesson from the earliest model to the latest, but we've already started this. This is a great model you guys devised from your bell work. It has all the stuff we need. We're just going to go back in time. The Bohr model, which is up here, this has these things literally orbiting. They're moving in a circle or in some pattern around, which we know is wrong, but it is easier to draw, so we do sometimes still use it. The Rutherford model, I'm going to switch colors because I'm You know what, actually, maybe I'll just, each time, I'll erase this, and then you can copy it down if you're watching the video, or if you're in here, you can copy it down when you watch the video again. We're going to keep drawing lithium-6 each time, just to make it, like, have a constant, consistency. So let's start that one over. So we had the quantum mechanical / probability type model. Let's do the Bohr model. Let's do the Bohr model. Where'd my black go?
It rolled under my chair.
Thing. The Bohr model would look like this. We would have separate protons and neutrons. 3 protons, 3 neutrons, 2 electrons in the first what we call energy level or orbital, and 1 electron in the second. This is the Bohr model, named after Niels Bohr. Okay, that's the Bohr model. The new feature of his, compared to the previous ones, was this idea of energy levels. Previously, you would have, I'm going to just keep going through this kind of fast and erasing, but you can redo it on the video or you can look in your book. I know you guys are still writing, but I just want to get through this fast before the class ends. The previous model is probably the more famous, or the most famous. It would be the Rutherford model, and it would have them kind of orbiting in these outlandish, like this is still the symbol for nuclear energy, but this was the Rutherford model. And his model was that the nucleus is here within the middle and the electrons are around it. Not that they orbit in a specific direction or shape or energy level, but just that they don't exist in the same physical space as the nucleus. That was Rutherford's contribution. And he found this out kind of interestingly, or at least I think it's interesting. He found this out in an experiment with gold foil. He had this piece of gold foil, and he shot a ray of alpha particles at it. And if the previous model, which we'll talk about in a second, had been true, he would have found that most of those alpha particles bounced back into his receiver, and that's what he was expecting to find. But instead he found that most of the particles skewed, or really most of them, the majority of them, just went straight through, which tells him that this thing is mostly what? Which it is.
Empty space.
Empty space. It's mostly empty space. So his experiment showed that it's mostly empty space, and that there's a concentration of positive charge in the middle. So his contribution was mostly empty space, and that the nucleus and electrons are separate. Going back one more. Let me make sure I get them right, because I get these two previous ones confused sometimes. Well, their names I get confused. Thomson's model, which is sometimes called the plum pudding model, I believe is what we're looking for next. Yeah, Thomson's model, which is also called the plum pudding model. So, it's Thomson / plum pudding. The contribution of this one, it wasn't mostly empty space, but he did realize that there were negative charges through something called the cathode ray experiment. The cathode ray experiment showed that at least part of the atom was attracted to a positive charge, which must mean that at least part of the atom had a negative charge. And he called those the electrons, or someone called those the electrons. It may not have been him. And for him, it was this positive charge matrix. It's called plum pudding. It's not something familiar to us, but in Britain it would be. The pudding part is this, and these would be the plums that are in it. I often call it like chocolate chip cookie model. Like this is the cookie is positively charged, and the chocolate chips are negatively charged, and they're interspersed throughout it. And you can see how.
Here's the interruption. Baby girls, we will be back.
You can see how Rutherford's experiment showed this to be false, because if his experiment had gone the way he thought, they would have all bounced back, because it would be mostly positive charge, which would reflect back the alpha particles. And the previous one before this was Dalton's model. And this is really, we can think of the first model of the atom. It was just a ball. Just a ball of chlorine, or oxygen, or in our case, lithium. Each atom had its own special ball, and those balls interacted, but they were just a solid thing that took up space. You can see how the cathode ray experiment disproved this. Having part of it be negatively charged shows that this is false. And we wouldn't even call this a model, but the only thing before this was that a man called Democritus thought of the word atom. This is ancient Greece. Dalton's was in the 1700s. This is ancient Greece. And he thought of this word from the Greek words how do you do the M? There we go. I think S's or sigmas or like that, which means A, like asexual or abiogenic means what? What's the A in that mean? Not, or without. And tomos means cut. So without being cut. His was just an idea that if I have this piece of cheese or carrot or goat and I keep cutting it in half, will I ever get to a piece that I can't cut into half anymore? And his thought was, yeah, of course I would. I'd eventually get to something that could not be cut any finer, and that is the atom without being cut. Cannot be cut. Does that make sense? So his was just an idea. Had absolutely no evidence for this. He wasn't a scientist. He was a philosopher. But then when Dalton came across that this is actually true, and by the way, Dalton's evidence was that these things always combine in set ratios. So lithium always combines with one chlorine and not the other, or not 5 or 6. And he just attributed that to Democritus. He said, we're going to call it the atom like that old guy did. Questions? You have your chapter review?
We're going to